Okay. Good morning, everyone. We are starting. I hope you can all see the screen.
Sir,
Yeah.
actually, your
Quite low, sir. Can you just very feeble, sir? Actually,
Yeah. Sorry.
your voice is actually very feeble. Can you just raise your voice?
No, I cannot hear you clearly.
Can you hear me?
I can hear that you are speaking, but I cannot clearly hear the words. Yeah. So what is it that you wanted to ask? This is the last slide of last class. Okay. So we had, if you recall, we had proved, we were showing that phi of x given by this formula is actually a stationary probability distribution to complete the proof in the case of finite state space. So we were proceeding with that proof. We had proved uniqueness even when S is countable. All right. So, and we had proved this part that it is a phi of x defined by that recipe is a probability distribution. And since S is a finite subspace, finite state space, all interchanges of summation and limits are justified. So now we will proceed with this thing of showing that the pi given by that formula is a stationary probability distribution. So you remember in deriving this, we had used that corollary in the earlier Markov chains, 7 or something. Here we will be using it twice, not just once. And using similar arguments, we will see that we have to show that this is equal to 1 over my. That is the idea of showing that pi is a stationary probability distribution. So summation over x of reciprocal of mx times pxy is equal to this. And in this equation, you are using the corollary, the set corollary of Markov chain 7. 1 over mx is equal to limit n going to infinity of 1 over n gn zx. Again, since S is a finite state space, all this interchange is all valid. So you have this. So remember here, summation is over x, varying over the state space, yes. Now recall an exercise which was given earlier, where you were asked to show that G sub n is equal to summation k going from 1 to n of P super k. Now notice here, this is P super k zx, and you are multiplying it with Pxy and summing over x varying in S. So this summation over x, this times this, that is precisely P super k plus 1 zy. So notice here, k is running from 1 to n plus 1 of this. Because now we have, but then k starting from 1 means here you start only from P super 2. So what is this k going from 1 to n P super K plus 1 ZY is precisely G sub N plus 1 ZY minus P ZY, the term corresponding to when this is equal to 1. That is to be subtracted. And now this PZY is dominated by 1. So that divided by n will go to 0. So this limit is same thing as limit 1 over n G n plus 1 ZY. And again, now apply the corollary that corollary we had been talking about again. So you get this guy is equal to 1 over my. And this happens for every y in S. Please note it down. So this shows that pi is a stationary probability. We have already shown it's a probability distribution. So this is the stationary property according to the definition of a stationary probability distribution. So we have this. So this completes the proof when S is finite. Okay. Next, in the form of a remark, I shall outline the proof when S is not necessarily finite. Of course, in this, we will be using, what you will see. The finite will approximate S by finite sets from inside. That is the argument, basically. But there are some steps which we have to be careful. Okay. So now let Z be an arbitrary element in S. And let S1 be any finite subset of S. This Z need not belong to S1. And since P super K is a stochastic matrix for every K greater than or equal to 1, what we have is, if you take 1 over n, G sub n Zx with X varying only over the finite subset. So this is a finite sum. So this, by an earlier exercise I was alluding to, that is precisely summation K going from 1 to n P super K Zx. So taking the summation over S1 inside. So this is, look here carefully, summation with X varying only over S1 of P super K Zx. Therefore, in this summation, X not belonging to S1 are excluded. So had they been included, this sum would have been 1. But here, since they are excluded, this is strictly less than 1. Not strictly less than or equal to 1. We cannot claim that is equal to 1. And this happens for every finite subset S. And of course, every Z in S. And every n greater than or equal to 1. Note it down, please. Now here, since this sum over S1 of this guy is dominated by 1 for every n, for the limit also that domination holds as n goes to infinity. So now you use the arguments as it is given here. And so therefore, therefore one will get summation over x varying over a finite subset of 1 over mx is less than or equal to 1 for every finite subset. Consequently, the summation over entire S of this is also less than or equal to 1. Note here, this is star and this is asterisk. But they concern similar things, so I have taken the liberty of using similar symbols, hoping that there will be no confusion. So when S is not necessarily finite, we have shown that 1 over mx summation over x varying over all of S is dominated by 1. Of course, we should get equality here. That we will see soon. Soon meaning later. Okay, well, proceed further. So in a similar manner, we can show this. So to sort of convince you, we will go back to that particular slide in the finite case. Yeah. So if supposing here we sum it over S1, where S1 is a finite subset of S, and S is not necessarily finite, countable case. This step, this up to this go through. as they are equal, equal, equal. Now here, since S sub 1 will be a finite subset, again interchanging the order of summation doesn't matter. So once you do that, what you will be doing is you will be taking P super K Zx Pxy with X being varying over only over S1. And all are non-negative terms. Consequently, here this can only be less than or equal to. Z and Y need not be members of S1. They can be arbitrary elements in S. So here you will have less than or equal to in that case. So with that, let us go back to that slide. Yeah. So because of that, you will see if S1 is a finite subset of S and Z and Y are arbitrary elements in S and N is greater than or equal to 1, then you would get summation X varying only over that finite subset S, S1 of 1 over N Gn Zx Pxy is less than or equal to 1 over N times Gn plus 1 Z minus Pz. So you proceed afterwards. Say this this is bounded by 1. So this divided by 1, n will go to 0. And this divided by n, as n goes to infinity, we know that that goes to 1 over my. So proceeding and as in that earlier derivation of double star, we get summation over X varying over S1, 1 over mx Pxy is less than or equal to 1 over my for every y in S. Here the summation here is only over S varying over X varying over S1 for any finite subset of S. You may note it down if you want. Okay. Consequently, you will get this. Since this happens for every finite subset, and here there is no dependence on that S1, you get summation over X varying over the entire S of 1 over mx Pxy is less than or equal to 1 over my for any y in S. So this we denote by double asterisk, hoping that there will be no confusion with double star. Okay. So what we had denoted by asterisk, by that we have this. So if you take summation over y, all y varying over s, that single asterisk guarantees that that summation is finite or less than or equal to 1. So by the single this thing, sum over y of the right hand side of this is finite and is dominated by 1. So using this by fairly elementary argument by contradiction or something, one can show that strict inequality in this cannot hold for any y in S. So this argument we are not going into. It is not very difficult. It is fairly simple. Consequently, what it means is that equality holds here. So when equality holds in this double asterisk, that is same thing as the double star for S in the denumerable case. So what we have achieved so far, when S is not necessarily finite, when S is not necessarily finite, it is, let's say, countable, double star holds for every y. That we have shown up till now. We have also shown this sum is less than or equal to 1. So to complete the proof in the case of countable S, we have to show that this equality also holds. But what we have shown is that this converges. That sum is less than or equal to 1. So we will call that limit as C. Yeah. So the defining property of stationarity holds even when S is denumerable, not necessarily finite. So since we know that by single asterisk, this guy is converging and less than or equal to 1, and of course it has to be greater than 0. So this inverse makes sense. So now you define a new quantity, nu sub x equal to C divided by mx. So therefore, since this guy converges to C, that is C, 1 over C times this, that is precisely this, that is a probability. This nu x, you can verify, nu x is a probability distribution on S. So this is a probability distribution, and so that we also know now that this is a stationary. So you can easily show that this nu x is a stationary probability distribution. But when we started with the proof, we proved uniqueness first. And that was given for general denumerable S. And in that, we showed that if there is a stationary probability distribution, that has to be of this form, 1 over m. So consequently, this mu agrees with our pi. That means this C is equal to 1. So this gives you an idea of the proof when S is countable, not necessarily finite. Okay. So that completes the proof of the theorem given in the general case. So yeah, small proposition or small result, small theorem you can say. Let Xn be a Markov chain on a denumerable space, yes. Let C be an irreducible closed set of positive recurrent states. C may be finite or need not be finite. It is a subset of S. It is an irreducible closed set of positive recurrent states. Then this result says then Xn, that Markov chain Xn, has a unique stationary probability distribution pi. Of course, that is defined on the whole of S, but it is basically concentrated on C. So what this means is there is a unique stationary probability distribution pi on S such that for X not belonging to C, that assigns the mass 0. So it is basically given by, in view of our earlier theorem, pi of X equal to 1 over m sub X for X in C, and it is equal to 0 for X not in C. You can easily check that this pi sub X is a probability measure on C, probability distribution on C, on X, on S, but it is basically concentrated on C. C complement has probability 0, pi probability 0. Please note it down. Proof is quite simple. This Markov chain restricted to C is basically an irreducible positive recurrent Markov chain with state space C. So apply the previous result to this thing to get the result. So any questions? Okay. Let us look at one example. Let PQR be numbers in the closed unit interval 0, 1, such that P is strictly positive, Q is strictly positive, and R is greater than or equal to 0. But they add up to 1. P and Q are strictly positive. So you apply the theorem in Markov chain 6 concerning unrestricted birth-death chains on Z. Remember, for the simple random walk, we had R equal to 0. So this, if R is not equal to 0, this comes under birth-death chain. So with Pi equal to P, Qi equal to Q for all I. Therefore, Ri equal to R for all I. So there we had seen the birth-death chain on Z is recurrent if and only if P is equal to Q. So in particular, the simple random walk is recurrent if and only if P equal to Q equal to half. If P is not equal to Q, I mean, even in this situation, then the Markov chain is transient. That means all the states are transient. Of course, this is irreducible Markov chain. And since P and Q are assumed to be strictly positive, it is irreducible. So all the states are transient. And hence, this Markov chain cannot have a stationary probability distribution. Please note it down if you want. Excuse me. Now suppose P is equal to Q. We will show that the Markov chain cannot have a stationary probability distribution in this case as well. Because that is the only case which is left, right? Because that is recurrent if P is equal to Q. And you remember that by an earlier theorem, positive recurrence sort of guarantees existence of stationary probability distribution. So positive recurrent state, a state is positive recurrent for that. By definition, initially, I mean, it has to be a recurrent also. We have defined positive recurrence only for recurrent states. For other states, it really doesn't make sense. So we will take up the case P equal to Q. Suppose P is equal to Q and let pi be a stationary probability distribution for the Markov chain. We'll prove by first. We are going to prove it by contradiction. Okay. So since this pi is assumed to be a stationary probability distribution, by the defining equation for stationarity, we should have pi sub j is equal to summation over I pi I pij. Since this is a birth-death chain, for a given j, the pij is non-zero possibly only for I equal to j minus 1, I equal to j, and I equal to j plus 1. All the other, for all other i's, that is 0. Therefore, this sum reduces to just the sum of these three terms. And P sub j minus 1j means in single step, it increases from j minus 1 to j. And that probability is P. And similarly, you have these things. Pjj is R, Pj plus 1j is Q. And since R is equal to 1 minus P plus Q, replace that, then you get here things involving only P and Q and the pi j's. Note it down if you want. So by fairly elementary rearranging terms, etc., which we have also seen long back while discussing recurrence and so on. And since P is equal to Q, so you can verify that pi sub j plus 1 minus pi j is, since this is equal to 1, you will get is equal to pi j minus 1 for all j in Z. So for pi to be a stationary probability distribution, in this and consequently in this derivation, we have used only the defining property of stationarity. But for it to be a probability distribution, all the pi j's should be greater than or equal to j. Oh, so there is an I missing. So please, and they also sum up to 1. So in particular, summation over pi sub I, summation over I. See, please, there is a typo here. This is pi sub I. So summation pi sub I in particular should be finite. It should converge. Of course, we require a stronger this thing that should be equal to 1. But we will arrive at the contradiction just even using that the summation pi I is finite. So verify that the only way these two guys can hold is only when all the pi j's are 0. The way to prove it is one way. Say, if this converges, summation pi I going from, let us say, 0 to infinity also converges, because all the terms are non-negative. So if it converges over the entire this thing, summation over z, it also converges over non-negative integers or positive integers. So if you sort of, let us say, take it from 0 to infinity, put pi 0 is some number. Therefore, pi 1 by this recipe will be something like that plus some c may be positive or negative. And then pi 2 will be pi 0 plus 2 times c, and so on. So the only way that thing can converge is when c is 0. And by the same kind of argument, it also, you will get that pi 0 also has to be 0. If c is 0 but pi j is not, then all the pi 0, pi 1, pi 2, etc. are all the same numbers. So that again, summation cannot converge. So I have given orally how this verification can be done one way. So yeah, sorry. Yeah, I think what I wanted to go backward. Right. We have shown that this Markov chain, even when P is equal to Q, cannot have a stationary probability distribution. And it is an irreducible Markov chain. So this cannot have a stationary probability distribution because that summation over I pi a is not equal to 0. It's not equal to 1. So no state in the Markov chain can be positive recurrent. If there is one state which is positive recurrent, since the Markov chain is irreducible, every state has to be positive recurrent. Consequently, all the states in this Markov chain, when P is equal to Q, that is all the PIs are equal to QI, is null recurrent. In particular, the simple symmetric random walk, that is P equal to Q is equal to half, that is also null recurrent. So here is the example of a Markov chain on an infinite state space, namely Z, which is in which all the states are null recurrent. Noted. This is the last slide for the day. If you want me to go back to any of the previous slides, I will do. So if not, I shall stop sharing and we will end the session if there are no questions or comments.
So, sir, is today's class over?
Yeah,
Okay. So, what will you do next class?
we will start looking at convergence, the limiting distribution.
Okay, okay. Means from Wednesday, right? Okay, 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 fine. So, am I audible now, by the way?
Yeah, now you are audible, but earlier you are not.
Okay, okay. Actually, then my mic was quite a bit low. I did not check. Okay.
It doesn't matter.
Okay, 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 okay.
All right. So we will see you on Wednesday.